Okay, lesson 5.5, 5.10, 5.11, 5.12, wrap up, part two. Okay, so I mentioned on here to complete the graph worksheets I gave you, and then to work all the kinetic molecular theory worksheet. The kinetic molecular theory worksheet looks like this, and I'll probably start off pretty soon with that, or an example like it. Let me show you. Okay, first of all, the notes were right near 5.12. What do we mean by kinetic molecular theory? As I mentioned yesterday, or in the other lesson, I did it yesterday, molecules are always in motion. They always have kinetic energy. And so, based on some assumptions that are made, the gas laws, like PVRT, was able to be derived. It's important to know that PVRT, first of all, it's not really a law. A law would mean it could never be broken, like gravity, calculating how much gravity, what will your weight be here, any distance from the earth, what would your weight be, how fast would you fall. That is a law. We could figure that out, okay? I mean, if air were taken away, it'd be perfect. The only thing that might interfere with the law is the air resistance, but even that will follow, you know, we can calculate that as well. We know the density of the air and all that. Well, anyway, I'm just talking. So the PVRT is based on 4 assumptions here. I have 4. Now, if you were at the UCLA program on a Saturday when we did this as well, there were some really good notes handout on that. In that lesson, let's see, I put, trying to see how I organized it. Yeah, it's the same thing. I put 4 assumptions of the kinetic molecular theory. I might actually talk about some of these examples that we did at that one. I'll draw them up here and I'll show you. I thought they were pretty good. But anyway, so first, let me start off with it. Number 1 assumption is this. Particles of gas are so small, we assume that, compared to the distance between them, that we can assume, that their volumes to be 0. Now that's really crazy. What it tells us is this. In PVRT, all right, let me tell you, like for example, if I had, well, let me just try to get, I just spilled this mess everywhere. I'm still using this in here. Still got it in my room from the other day, a few days ago, UCLA. Here, you see I've got about 22 milliliters of water. Has food coloring in it. 22 milliliters of water with the green food coloring. Okay, that is exactly how much liquid I have, 22 milliliters. If you had a block that size, you could say it's 22 milliliter block or 22 cubic centimeters for a solid. We use that a lot. But now, gases are different. When we say, your container is 22 milliliters of gas, you don't really have 22 milliliters of gas. In PVRT, this is not really the volume of the material. It's the volume of the container, the amount of space that molecules have to move around in. So for PVRT, let's just say I've got a cylinder here. We assume that all the molecules, they're like dimensionless points, okay? Because we're saying that if these molecules, well, you can't even see that at all, but we're assuming that they're dimensionless points. If this is a big tank, like a helium gas tank or whatever, this say it's like an 8-liter tank, well, we would be saying, the gas molecules, you have 8 liters to move around in. Well, that's not really true if you think about it, because all the molecules themselves take up some volume, so they can't really have 8 milliliters to move around in. They have something left. Maybe they have 7.999 or whatever, but they don't have 8 full milliliters. Okay, but anyway, number 1 assumption is that gas particles are so small that we consider them to be, their volume to be negligible. Now, why do we do that? Because in everyday conditions of temperature, pressure, anything you'd work at on Earth in a lab, even if it was hot temperature, cold temperature, high pressure area on the mountaintop or in the valley like Death Valley, in all these situations, PVRT should be okay in normal conditions. If you can live and breathe in those conditions, then most likely PVRT is fine in those conditions. But there are some extreme conditions where it doesn't work. All right. Anyway, I'm just telling you what the theory is based on. Number one. Number two, kinetic molecular theory says gas molecules are moving in constant straight line motion. Now, we assume that they move in a straight line motion until they strike some other object, and then when they strike it, of course, and they change around, but they perfectly rebound and change around, as you see, on and on and on. All the molecules are doing that. Now, in reality, okay, we assume that all collisions are perfectly elastic. There's one more thing I don't think I wrote on here. And that is, you could add in there that pressure is caused when a molecule collides with the side of the container. That's where we get the pressure. Like, so it's probably better to think about not a cylinder, but like a balloon. Like when you're holding a balloon or a tire for a bicycle tire or a car tire, you pump it up and you feel that, and you get to a point where you put in the air and you realize, hey, the tire is not getting any larger. So it's at the volume is pretty much set, but if you hold it and you continue to put gas in, you notice it gets to be more and more and more tougher, a lot more durable, harder. I'm trying to say. So what's going on there is the pressure that it gives you, that you're feeling when you push on it, is caused by the molecules colliding with the side of the container. Now, so if we say the pressure inside here is, we'll make it up 3 atmosphere, okay? Or how about if I use a tire pressure? A lot of tires have like 45 PSI, they call it, pound per square inch. You could use that as well, like a bicycle tire. So if that's the pressure, it means that's the pressure that it's striking on the outside of the container or in the tire or whatever. And for that matter, when a molecule strikes another molecule, it's also giving that same pressure. So it's the same throughout. You're getting the same pressure all around. But pressure is caused, we assume in the ideal gas law, pressure is caused when the molecules collide with the side of the containers. Okay. I forgot to mention about elastic. I don't have a ball in here to show you that. Oh, it's the best way to do it. Well, anyway, what elastic would mean, a perfectly elastic collision. We assume that all collisions are perfectly elastic. No energy is lost or gained as they move back and forth. If you take a basketball, and let's say right now, if I had one, I would show you, but if I drop that basketball right now, it'll hit the floor, it'll bounce back up. Will it bounce exactly right back up to my hand? If I just let go of it, boom, will it come right back to my hand? No, it'll come back a little bit lower. Then, all right, or if I don't touch it at all, it'll come down, it'll bounce down, come up a little bit low, not quite as high, a little lower, bounce again, a little bit lower, bounce again, a little bit lower, bounce again, a little bit lower, okay? My fist became the ball. So anyway, that's because that is not a perfect elastic collision. A perfectly elastic collision would mean it would come right back to the same point. No energy would be lost in a perfect elastic collision. So that's where we're getting at. PVRT assumes that when they collide, no energy is lost. Or I don't really want to say the word lost, but I'll say transferred. It's really transferred as heat to somewhere else. But the energy stays within the system. We assume that. Now, again, in everyday conditions, it's okay to assume that. There's one more thing, and I'll throw it in now because it's going to come back in a moment. Actually, it's number 3. I was going to throw it in, but it's number 3. Number 3 says, we assume there is no attraction between molecules. Molecules are assumed to exert no intermolecular force of attraction. Now, we're going to talk about intermolecular forces in an upcoming chapter. Chapter 10, actually, okay? And we'll be there faster than you think, but anyway, but because chapters 8 and 9 are combined, and 7 is 7, 8, 9, 10 have no math, almost no math. You'll really be happy about those. Okay, but let me show you this. So as molecules move around, what happens is we know that molecules attract to each other. Water molecules attract. If you have H2O, water vapor, like in the steam, like in the bathroom, you have a shower, bath on, whatever, and you have the steam in the room, that is water vapor. We know that water vapor can hit something cold, like the mirror, and you can see droplets on it. It can condense. So gas molecules can come together. When they come together, my kids are going crazy there. When they come together, they become a liquid. They condense into a liquid. All right. Why do they stick together? Because they have what's called well, like magnetic forces, we'll call it that. It's polar forces of attraction. So molecules all have attractive forces. All the gas molecules do. Some are very strong, some are weak. Well, here's the thing. Gas molecules also move very fast. So if they're moving really fast, it doesn't matter. They're not going to stick together. That's not going to happen. All right, they're uninfluenced by it. But now, if they start to move slow, then we got a problem. Well, PVRT's got a problem. But so PVRT assumes there's no attractive forces. Again, in everyday life and all of our conditions, we don't have to worry about that. It's true. But when molecules go really slow, now they start to stick together a little bit. And if they stick together, that means their pressure when they hit the outside is not going to be as strong as we expected it to be. So PVRT ignores that little part, okay? And the fourth one just says average kinetic energy of a collection of gas particles. Average kinetic energy is assumed to be directly proportional to its Kelvin temperature. Or another way to say it is, Kelvin temperature measures how fast the molecules are going. We assume that. Now, that is not 100% true. I told you, well, temperature is a measure of average kinetic energy, but it's not 100% true. We don't have to get into why. Okay, so all four of those things are assumed to be true, kinetic molecular theory, and from that we get PVRT, among other things. I'll talk a little bit more about that. And it works fine in most conditions. There are some places where it starts to fail, and I wonder if I should talk about that right now. Maybe I will do that, and then I'll get to the worksheet. I guess I'll do that. So what happens is this. Okay, and I'm going to 512. I was actually at 511, but they're kind of together. This scientist, van der Waals, what a last name is that? Van der Waals. Johannes D. van der Waals. And there he is right there, van der Waals. There he is younger, and there he is a little bit older. Okay, so he there's a whole lot that he did with for chemistry, and you'll see him come back in a later chapter. But most of his work dealt with describing intermolecular forces, which I just showed you a moment ago. Now, and I'll talk about that. Intra, what do we mean by intra and intermolecular force? I think I've mentioned this in an earlier lesson. But like water, and we'll talk about this in another chapter when we do Lewis dot diagrams as well. One water molecule, oxygens have a negative charge where these electrons are. That's electron pairs. And a positive charge by the hydrogens. So hydrogen's positive, oxygen's negative. Just like on the chart, H is +1, O is -2. It's actually related to that as well. It has to do with the nucleus and attracting electrons. But here there are electrons in the bond. But one water molecule can attract and line up with another water molecule. And I almost drew it wrong. The oxygen of one molecule will attach to the hydrogen of another. Now, and then one might do over here as well. An O will come here, and then an H there. Let's just say an H there. Okay, so what do I have here? If you have ice, these things will be perfect symmetrical alignment, incredible. Like, you've seen crystals and how they look. It'll be perfect geometrically amazing if you have ice, okay? But if you have liquid water, they won't be perfect. And my drawing is probably not perfect. I can make it look even less perfect if I kind of do it like this. So say you have a molecule there, there, and there. They're able to move around, but there's like there's a strong magnetic attraction here and there. We call it magnetic. Polar attraction is what we call that, really. So here's the deal. This is called an intramolecular. Intramolecular would be a bond. The bond from O to H. That one or that one. That one or that one would be intra, or that one or that one, or that one or that one. But from one molecule to another molecule, we call that intermolecular forces. Like I showed you the diagram of molecules moving around. I put a little green force field around them, kind of attractive field. That would be the intermolecular. Think about the interstate. The interstate, that if you get on 10, we said the 10 freeway, I-10 means interstate 10. If you get on it in Santa Monica, the ocean, you go all the way across east, across the U.S., you'll end up in Jacksonville, Florida, at the other ocean, the Atlantic Ocean. So it connect interstate goes from one state to another. Intermolecular forces connect one molecule to another molecule to another molecule. When you melt ice, when you boil water, what happens is this: you completely detach all the water molecules from each other. So there's no longer any hydrogen bonds. Oh, I didn't tell you that's actually called a hydrogen bond. But we're going to get that plenty in a later chapter. But anyway, they completely will detach. So intermolecular forces are what breaks apart. When you boil water or you melt ice, you do not break it up into H and O. No, that would be a decomposition. No, that doesn't happen. That would be breaking intramolecular force would be if I decompose water into oxygen and hydrogen. And that can be done with electricity. But anyway, okay, so I'm jumping off track a little bit there just to give you that. So van der Waals studied intermolecular forces, and he also he came up with an adjustment to PVRT. How can you make this work for the real life situation? So I've kind of already mentioned this, but I'll just tell you. There are two conditions where PVRT starts to fail. And it's on this page right here. This is kind of the more important thing. It fails when gases are at very low temperatures or when they're under very high pressures. Okay, so if a gas is under a very high pressure, so let's put a cylinder here, and I'll put a cylinder here. And we'll have a piston. So when I say a piston, it's like saying like in a syringe, okay? You're able to move this thing. Oh, well, my drawing wasn't too bad, but I forgot to make one with a smaller volume, one with a higher volume. Okay. Now, so let's just say if I put 1, 2, 3, 4, 5, 6, 7, 8. Let's put 8 molecules there. You know what? I kind of like to draw them even smaller. Oh well, just to kind of show you my point here a little bit. But that'll be okay. And then here I'll put them. Okay. So here's the thing. In most situations, PVRT works fine, but it fails if you're at low temperature or if you're under high pressure. What happens at low temperature? All right, PVRT fails low temp or high pressure. Okay, what happens at low temperatures? Molecules move really slowly. So if they move slower, then they're more likely to stick together. And remember, we talked about that. If they stick together more, if they're sticky, they're sticky. I'll just say they're sticky. If they stick together more, then their pressure is not going to be as high as PVRT would assume it would be. What will happen is if you measure a pressure in a lab, it'll be a lower than what you expected. Because in a lab experiment, if it's really, really cold, you might say, hey, PVRT, it says the pressure, if I use PVRT, the pressure says it should be, we'll say 3 atmospheres, but I'm only measuring it to be 2.95 atmospheres. It's a little bit lower. Why is it, in real life, why is it lower? It's because they're sticking together a little bit. So when it's colder, okay? Now, the other time is when you're at high pressure. Now, under a high pressure, can you notice you also have a low volume? High pressure pushes all the molecules closer together, okay? So you also have a low volume. Now, when there's a low volume, can you remember the other thing I told you? Remember, V in PVRT stands for the volume of the container, the volume it has to move around in. It's the volume that a molecule can move around and do work in. Well, here, let's just say that in this case, this might be 5 liters, we'll say, and now here we might say it's only like 2 liters. Well, the thing is, we still have 8 molecules before and after. In which one is it more true? Well, I'll say more true. In which, the first or the second diagram, where is the is this closer to the real volume, or is that closer to the real volume that they have to move around in? you could say, well, maybe I'm saying the question wrong, but I'll just make it a statement if that didn't make a question out of that. Here, the 8 molecules, we say that this container has a volume of 5 liters. Well, that's a lot closer to being true because they're far apart. Here, we say it has 2 liters to move around in. Well, now that's not so true because the molecules themselves might nearly be 1 liter. I mean, I drew that weird in the picture, but I mean, molecules won't be that large. But if I did, look at that. That might be close to like 1/3 or I mean, close to almost a whole liter right there. So then we'll say, well, do you really have 2 liters to move around in? If this is 2 liters, this space, do these molecules really have 2 liters to move around in? And they don't, because they only have this volume minus their own volume is what they really have to move around in. Okay. Well, I guess that's just a way to kind of think about it. So know that PVRT fails in those 2 conditions. So what van der Waals did was he made, well, maybe I want to keep that picture up in case it comes back again. I don't know if that will, but But anyway, here is the van der Waals equation. P, now you don't have to memorize this equation, but you do need to, it is useful to be able to explain some things out of it. N squared A over V squared times V minus NB equals nRT. Now, why in the world do we need that crazy thing? Okay, remember what I said. First of all, I'll tell you this. This used to be on the AP exam. This used to be on the formula sheet. They never had made anyone make a calculation with that. And I'm not going to do that either, okay? I have done it before when we first started teaching, when I started doing AP like 15 years ago. But I actually, you know what? I'm wrong. It was 20. I did, one year I taught it for just an overflow class. It was the first time I ever did it. But anyway, so I did make some people do that, use that equation. But anyway, first let me tell you this. They've never really had you do any calculation on the AP with that. But they do ask you to explain this equation. And that's kind of that's why I'm spending a lot of time on it. So here's what might be useful. I'm going to put the pressure that we see in the lab and the volume that we measure in the lab. Lab measured. Uh-oh, my word measured doesn't look too good. Okay, lab measured. Okay, so here's the deal. And this will make sense in a minute if you see the word lab measured under P and under V. All right. First of all, we'll go with the volume because that's kind of the easier one to get. According to PV and RT, if you solve V, that's the volume, the container, the volume that it has to move around in, the molecules have to move around in. Well, in reality, when you're under low temperatures or high pressures, and it doesn't have to be both of those, but it can be just one of those. Like high pressure, you can get that to be like a really, really high pressure chamber. We can see that PV and RT starts to fail. But anyway, in these conditions, the volume that you measure in the lab is going to be bigger than the real volume of molecules have to move around in. I just showed you that a moment ago. So the volume, like if you have 8 molecules here, if we said this is a 2-liter volume, right? This level's 2 liters, and we move it up here, it's 5 liters, and 2, 3, 4, 5, whatever, something like that. I just kind of made up numbers. If we say it's 2 liters, that's not true. In the lab, we say it's 2 liters. Okay, the lab measured is 2 liters, but in reality, it's going to be it's smaller. The volume it has to move around in is smaller. So what you have to do is you have to subtract the volume of the molecules. And so N stands for moles, and B is called a van der Waals constant that has to do with volume of a molecule. Now, I'll just tell you that every gas, like say if you have CO2 or H2O vapor or O2 or N2, they all have their own value for the van der Waals A constant and the van der Waals B constant. And I don't know what the numbers are. I mean, 20, 1.5, I'm just going to make up some numbers. I don't know what they are. They all have their own value. First of all, this would be the volume of the molecule. So obviously, a bigger molecule times the number of the moles times the volume, you subtract that. So if I subtract out the volume of the molecules, now I'd say, oh, in reality, you don't have 2 liters to move around in. You have, take away this volume, I mean, you have 1.20 or whatever it might be. You subtract out. Okay. All right. The other part of the van der Waals equation adjusts the pressure. So in this side, as I said, remember, in the lab, you'd measure, the pressure you measure in the lab would be too low. Like you'd say, hey, according to PVRT, at this temperature, the pressure should be, 3 atmospheres. It's whatever, it's 75 degrees Celsius. Really pretty, that's pretty hot actually. 75 degrees Celsius in this chamber, the pressure should be 3 atmospheres. Okay? Oh no, I shouldn't use a hot temperature. I should use a cold temperature, low temp. Oh, okay, let's change that. It's really cold. How about we'll go down to like 5 degrees, almost freezing. We'll go to 1 degree Celsius. It's 1 degree Celsius. If I use PVRT and I put in 1 degree Celsius right there, when I solve for pressure, it says it should be 3 atmospheres. But wait a minute. My answer in the lab, it comes out to say it's only 2.50 atmospheres. Oh no. Why is that? Why does the lab only say 2.50? It's because now they're going so slow that molecules are being stuck together, and so they don't hit the side as forcefully. Okay, so anyway, the bottom line is, if I use the van der Waals equation, then I can take my low pressure in the lab, 2.50, and I'm going to add to it the this side. This will be the number of moles times A is the van der Waals constant for intermolecular forces. Okay, and then that's the volume also, again down here squared on the bottom. So we're not going to have to do the math of it. But the point is, you see that to adjust PVRT is not true, but under low temp, high pressure, if I take my lab pressure and I add this to it, and I take my lab volume and I subtract that from it, now multiplying those will be NRT. So it's an adjustment to make PVRT work. Okay, that's a lot of craziness there, and there is a calculation even in the worksheet on the notes, but I'm not going to do that. No, I'm not even giving you that worksheet either. So here's the last little thing. Now this part will be more fun. You'll like this part. And actually, let me get one thing. Good gracious. Okay. Sorry about that. I had this thing on and I heard people talking. Okay. All right. So now, I forgot to tell you something else. Okay. Before I go, well, as I'm doing the worksheet, I'll go over this. I need to talk about this little graph for a moment on the front. So I just realized there was something I left off, and that was the Maxwell-Boltzmann distribution, which is going to come, let's see. Oh, there it is, 510. It's 511. Okay. So yesterday, there it was. Yesterday when I went over the lesson, I forgot. I just stopped with that, and I didn't do it. So I'm kind of going back to 511, but okay, I know I'm jumping around a little bit, but I'll come back to kinetic molecular theory in one moment. It's all related anyway here. Okay, well, what these two scientists did, I'll make it real quick and easy. These two scientists, Boltzmann, Maxwell and Boltzmann, James Clerk Maxwell and, I can't remember, Ludwig Boltzmann, they figured out how would you graph a distribution of molecular velocities. What in the world does that mean? Molecular velocities for any gas, or for really any substance at a given temperature. And it's a really simple thing. I made a little graph grid on there for you. Oh, yours could be a little bit better than that. But guess what? It's a bell curve. If you've ever seen a bell curve, it looks like this. Now, what in the world is this? One thing that's important to know in chemistry is, for a graph, what goes on the x-axis, what goes on the x-axis, what goes on the y-axis. This would be number of molecules. Guess what? this could also be, imagine number of people. I'll tell you about that in a minute, but number of molecules. This would be the velocity of the molecules, velocity in meters per second, or it could also be the kinetic energy of the molecules. I think I wrote that on the, it could be the average kinetic energy in, we'll just say joules, okay? Or it could be kilojoules or anything like that. Because remember, you can, down here will go either velocity, meter per second, or kinetic energy in joules. Now remember, if velocity increases, your kinetic energy increases. Now, if your velocity increases just a little bit, your kinetic energy goes up a lot because you square on this side. You square your velocity, so it goes up exponentially, the kinetic energy. All right, but anyway, so either this could be velocity, and I'll just use velocity here. So we'll say, here's like, I don't know, I'll make up some 100, 2, 3, 4, 5, 6, 7, 800. So 0, 100, 200, 300, 400, 5, 6, 7, 800 meters per second. Really fast moving molecules. Okay, now what I'm going to do is, what it means is this. This is like a, I want to call it like, is it called like a bar graph? And what it means is, right here, let's just say that you have about 1, 2, 3, 4, 5, 6 molecules are moving at about 350 meters per second. That's their speed, okay? Then you have maybe 1, 2, 3, 4, 5, well, we'll fit one there, about 6 going that speed. 1, 2, 3, 4, 5, 1, 2, 3, 1, 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 1, 1. Okay. Well, anytime you make any data on a graph, anytime you graph any data with a bell curve, this will be true. The average is going to be right here in the middle. One of the best examples to do this is a person's height. If you got everyone, the more people you have, the better you're going to get a curve like this. But if you had everybody in the school line up from the shortest person to the tallest person or whatever, but you'd graph it. You'd graph it out. You'd graph out how many people are this height, this height, this height, this height. Well, it turns out that this is your average. Right around in the center is going to be your average height, or in this case, your average kinetic energy, or your average speed, velocity. In fact, can you remember that equation? Velocity, root mean square. Either this equation or this equation. We don't have to use them, but all I'm going to show you is that if you calculate it, that's what you're getting right there. You're getting the average velocity, VRMS. You might see that in college. You probably will. But the average velocity. So that what it means is this. Almost everybody, if we get the whole school graphed out, well, I won't say the whole school, but yeah, if we did, like, let's just say what's an average height, we consider guys and girls, adults, all the ages. Probably, you might say, well, the average height might be 5, what? I'm going to guess some number. Let's just say like 5, what could I pick? I don't know. 5'3". We'll just make a number, 5'3" okay? That might be too tall, but no, I think that's about right for an average. What it means is most people are going to be, in the school, will be near that height. Maybe that's more like a middle school, actually, that height, when I think about it. But oh well. Most people will be near that height, but some will be a lot taller, and some will be shorter, okay? A little bit of people, a few people will be really, really tall, way up high. A few will be a lot shorter right here. But most people will be right near what the average is. That's what a bell curve means, and that's what it tells you here. So most molecules are moving at about this velocity. So what will be the average kinetic energy? If you saw a graph like this, you'd say, oh, the average kinetic energy or the average velocity would be about 350. Well, the average velocity would be 350, we'll just say, somewhere around 350. The majority of molecules are moving somewhere near 350. But some are moving faster and some are moving slower. All right, that's how you would read the graph. Now, if you wanted to find out what is the kinetic energy, you take 350 and you plug it into there with the mass of a single molecule. Or you could use, I didn't know what that was, 3/2 RT, nRT, 3 halves nRT. That one's actually a little bit better. Okay, but anyway, okay. Oh no, you can't put velocity there. Never mind, you can't use that one for that one. Okay, we're not going to see those. 1/2 mv squared is the one you ought to kind of be aware of. Okay, now here's where it gets to, here's the way they like to ask questions, and I like to ask this as well. So let's draw a graph. It's actually on the next page. And we're just going to say here is A, and here is state B. State A and state B. And then let it be the same thing. Number of molecules is here. And then velocity is here. Or you can put kinetic energy. Okay, in joules. Joules or meter per second. They're all going to be going down there. I mean, maybe you could say it's 100 joules, 200, 300, 400, 5 joules all the way. I mean, the numbers would not be the same, but you'll see numbers increasing. Okay, so here's one question. From A to B, when it changes from state A to state B, this is the same gas here in the A to B. No gas escapes from it. Like say you have a balloon, you change this balloon from condition A to B. Where do you have a higher temperature? Is it A or B? It would be at B, because temperature is average kinetic energy. Here your average kinetic energy is right there, which if I'm using the graph above, it's about 200. We'll say 200 meters per second. But in state B, the average is about 350. Looks like it's about like that graph, okay? It goes from 200, we'll say, to 350. So here it has higher average kinetic energy. Now, why is it more flat? The reason is because, see, you have the same molecules, even at a high speed or high velocity, you still have some that are going very, very slow. One way, a sad way that I sometimes look at it is to say that on a test, okay, most people make right around this average amount. Like you might say, most people have near a C. That's usually how it works. In a lot of physics, chemistry, science, a lot of classes, especially when they involve math, a lot of people might be near a C. Some are really, really high A's, and some are really, really low F's. In fact, some people don't come to school very much. They're out a lot. Like every class I ever have. I mean, there's always somebody. Well, I won't say I've always had fails before. There are some times that I did have where everybody came and did their work, and there were some rare years where nobody at all failed, okay? But usually people just don't come to school once or twice a week, and you can't miss 1 or 2 days a week in a chemistry class or physics, and not many people can do that, miss it and catch it up. They don't do it. Is what happens a lot. Well, anyway, here's the point I was trying to make, that even at if I made a test really, really hard, then that graph, let's see. Well, the A would be a harder test, and B would be an easier test, because B has a higher average than A does, okay? But even when I have an easy test, that's what I meant to say. When I have an easy test, okay, and the average is really, really high, or even really higher, we'll look at part C, a really, really high average right around here on the test, there are still some people that make near like a 1 or 1 point on it, really, really low grade. But actually, it's because molecules, there's a limit. You can't go slower than 0, or nearly what we'll say, not moving. So there's a slow limit this way that you're always stuck with. Okay, an easy way to remember this graph, and I should have told you this before. Here's a quick, easy way that came from the teacher before me, Richard Erdman. And he would say, here's a way to remember it. It's called the ice cream graph. If I took a scoop of ice cream, I rolled it up, and I rolled it into the corner, like on the floor, into the corner. Just so you got this big scoop of ice cream right here in the corner, right? It hits this boom, it just hits the side there. As it melts, what's going to happen? As the ice cream melts, it's going to, well, I guess he'll draw it a little bit curved, a little ice cream right there. As the ice cream melts, it's going to get flatter and flatter and go down, down, down. So here it was cold, we'll say cold, low temperature. Now it gets warmer and warmer, and then finally it's going to be a puddle. So the ice cream graph is an easy way to remember that. Okay, all right. I am just going and going and going. If you want to pause into this and come back and see it, you can. But see, there's no math in here, just explaining some things. But now, this is the more fun part, I guess, where I'm going to talk about how to work these worksheet graphs. Okay. So, I didn't mention, I forgot to show you. So on my graph, if I go from here to the right, that would be increasing in temperature. What I've got to show you is, what if I did this? What in the world? If the point, the beginning and the end are the same, that means you had to add more gas into to the sample. So you added some gas in. So if you have A and B, B has more gas in the sample than A. Or if you let gas come out, then you might come down to C. C would have less gas molecules. Okay, so I think you can try and do these problems right here from what I've just told you. But now the next page, this is the good one, all right? About the gas being sealed in a chamber. Now, I'm going to show you two possibilities of this. And I'm going to use an example that came from our notes at UCLA, which I like. This works out as well. Okay, so let's first of all say I have a sample of gas. Oh, you know what? I'm going to need to get more space, I think. You can go ahead and take these away. You have two possibilities. It can either be in a rigid container, or it could be in a balloon or something with a movable piston. So I'll just put here, in a rigid container, all right, so like a can or something like that, rigid, or tank, metal tank. Even a glass flask is rigid container, okay? You might have a flat inside a rigid container, these gas molecules, or you might have it in a container with a movable piston. Well, I guess I'll draw that right below it. Now, I wish I could do this a little bit better to actually show you one of these. Like I talked about before, we'll just put some color in that a little bit so you can see it. Okay. So what happens is, in a container with a movable piston, then it's like saying you have a syringe, but it's capped off or clogged up, whatever. The pressure inside is equal to the pressure outside of the air coming in and hitting the top of that. So they're balanced. Now, if you it's like a balloon as well. A balloon also counts as like a movable piston, because the pressure inside the balloon will always equal the pressure outside the balloon. So here are all the factors I want to look at. If I change the temperature, let's just say that I increase the temperature of the gas. Well, what's going to happen to the number of moles of gas? What's going to happen to the volume of the gas? Okay. What's going to happen to the pressure of the gas? What's going to happen to the average kinetic energy of the gas? Uh-oh. I think I had a little bit more, I'm not sure, but there might be a little bit more here than I had on my worksheet. What's going to be the average velocity? We could say V average or RMS, root mean speed. They're pretty much equal to each other. You don't want to have to worry about when they're not. What will happen to the collision frequency? Frequency. Well, I'll put FREQ. I can't fit that. Oh, what's going to happen to the energy of impact of the molecules? Oh no. Energy of impact of molecules. And then the distance. Wow. I'm going to have to... okay. I want to have distance. I'm glad I did erase that. Collision frequency. Look at me. Okay. Velocity. Collision frequency. Energy of impact. Well, if you're in a classroom, just get to. And then the distance. Distance between molecules. Okay. Distance, BTW, right? Can also mean between, not just by the way. Distance between molecules, energy of impact, collision frequency, velocity, average or kinetic energy, pressure, volume, and then the moles. Okay, And so these are going to be the same factors. We look at all of them, but we might just say change. Okay, here we go. So I might use that same list for all of these conditions. I'll show you what will happen. So if I increase the temperature of the molecules that are in this rigid container, like a can, like the can I showed you the other day too, all right, what happens to the moles of gas? If I increase the temperature, the moles of gas will stay the same. Okay? They did not change. Nothing, no gas went in or out of that. What happens to the volume? It's also going to be constant, or the same. Constant. So moles the same, volume's constant, the same. What about the pressure inside there? If I increase the temperature, okay, when you increase the temperature, what happens is, kinetic molecular theory, the molecules are going to start to move faster. Since they're moving faster, they're going to hit the side of the container. Two things are going to happen. They're going to hit more forcefully, but also they're going to hit more frequently too. Okay, and I'm kind of getting to that later. So anyway, they're hitting more forcefully, so the pressure will go up. You will increase the pressure. Now, I just said this, I can jump ahead. The collision frequency will also go up. In fact, these two will always be tied together. Pressure, by definition, is based on the collision frequency. So if you're a higher temperature, you're moving around slower, like 1, 2, 3, 4. They're going 1, 2, 3, 4. They're all doing that a lot faster. So more collisions every second, and they're more forceful because you're a higher temperature. Okay. Now, kinetic energy is going to go up. Remember, kinetic energy. Hey, I got a neat way to do that too. But if I increase the temperature, watch this. It's going to increase the kinetic energy. Because remember, temperature is a measure of the average kinetic energy of the particles of substance. What about the velocity of the molecules? The average velocity of the molecules is also going to go up because, remember, kinetic energy is 1/2 mv squared. Now, what can happen on a multiple choice question is they can just ask you one of these or two of these. Like if I increase temperature, the pressure, like A, B, C, D, the pressure goes up, kinetic energy goes up. Pressure goes up, K goes down. Pressure goes up, velocity goes up. Pressure goes up, velocity goes down. So, you need to know how they're all tied together. The energy of impact, I already told you that one as well. At a higher temperature, you got more energy, so you're going to have a higher collision impact. It goes up. And what about the distance between molecules? Okay, notice this. If this moves around, if they're moving fast or slow, it doesn't matter. Gases are always going to spread out homogeneously, equally throughout to distribute themselves through a space. So it's the same. That stays the same. So you might notice that the distance between the molecules, I guess I could have used a yellow one if I had yellow. This will kind of tell you, I think I do have a yellow here. The volume's the same. The distance between molecules is the same. The volume and the distance between molecules will always be, they'll do the same thing. They're tied to each other. If the volume gets bigger, well then now the molecules will have more distance between them. Okay? All of these, temperature, kinetic energy, velocity, and energy of impact are all going to do, they'll always do the same thing. And then you have to memorize that. The green ones will always match. Well, I put green for moles. That's kind of a, well, I'll just keep that one. It is the same, but I don't want to say it's tied to anything on there. All right. Okay, so in fact, let's do that one next. So let's just say, what if I switch these two? I probably won't do all of these examples, but I'll do a good bit. Okay, let's just say I switch it. And now I'm going to put this to be the temperature and this to be the moles of gas. Okay, so if I increase the number of moles of gas, I increase the number of moles of gas. In other words, just like you're pumping up a tire. You take it there and you put more air inside it. So I put more air. Well, now look at what's happened. The picture kind of tells you. Sometimes a picture can help you answer these questions as well. The temperature is the same. Nothing happened to the temperature. Okay. They're not going to be. They're still moving the same speed. It's just you have more molecules moving around in there, so you have a higher pressure. When you put more air in your tire, the air didn't get real hot. Tire wasn't getting hot. Okay, no. If it did get hot from friction for a moment, just after a couple of seconds, it would come back to equilibrium. The temperature will be matching again. The volume is the same also. The volume, I'm just going to use this one color. The volume will be the same because the container's volume. the pressure is going to be higher because you have more molecules. Having more molecules mean you have more collision, more frequent collisions now because there's more molecules. So collision frequency goes up. Average kinetic energy is the same. Temperature didn't change, so it's the same, no change. Velocity average, it's the same. Energy of impact, it's the same. The distance between molecules is going to go decrease because now you have less space, less volume to move around in than you did. Okay, all right. Now, let's do the same thing. I'll tell you what, let's take the other one, like in a balloon. If you feel good about this, you can stop the video. This is all I'm going to do. I'm going to just tell you to work on the worksheet. Okay, so let's do this. Let's say now that I have my my movable piston, and let's say that in this one, let's increase the number of moles of gas. Okay, if I increase the number of moles of gas, again, this is like putting a bicycle pump in, pumping air into a balloon. That's like a balloon right here. You pump it, and guess what? It's going to rise up there. So you're putting more gas inside. And if I put in more gas, it was at that level, it's going to go up to a higher level. Okay? So the temperature, same, no change. The volume is going to increase. Okay? We'll say here, you put more gas in because it can push. Now, let's just think about this case. In this case, you add more gas, and it became a higher pressure. For a brief moment, there'll be a higher pressure. But then it will push to match the outside pressure, and it will continue to go until it matches the outside pressure. Okay? In fact, I just told you the answer to that one. It will stay the same. That's a strange thing. Okay? Because the collision frequency will end up being the same. Constant pressure. And maybe I wanted to bring that up as well. When you're in a rigid tank, that means you have constant volume. So if you're doing a PVRT problem or PVT, 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 in a rigid container, volume 1 and volume 2 are the same. They're equal. Well, in this one, pressure 1 and pressure 2 are the same. If it has a movable piston or balloon, that's spelled wrong, okay, equals constant pressure, okay? This is a strange one to talk about, and I'll try and show you here. So let's just say that here's the volume before, and it goes up to here's the volume after. So let's just say that this thing, the piston was here. I don't know how to draw that too good. I'm trying to make it quick, and it went all the way up to here. Let's just say that you had this volume before. You had a molecule. Think about one molecule only going, boom. Just say that. Can you hear that sound? That's the collision of the molecules. It goes up and down. Now you heat it up. So as you heat it up, for a brief moment, it's going to go faster. Now, since this is able to move, like say if you have a balloon, or you have something that can stretch, movable piston or balloon, you start it off at low temperature. Oh, we're not doing temperature. I'm sorry, but it's the same thing. It'll be the same idea. But you're adding more gas inside here. So now if I add, well, I should probably tell you it's temperature, but it's the same thing. If I put more molecules in, now you have, you're having more frequently. So it's gonna be, so what's gonna happen? You're having a higher pressure, putting more gas, and so they're gonna keep stretching it up there. They're gonna keep stretching this thing up higher. I'm gonna talk about temperature for a minute. It's the same basic concept. Temperature, 1 every second, we'll say. It's hitting. Now I go higher temperature. So it stretches. So when it get at some point it will stretch. It will continue to stretch outward until it matches the original that you had. So even though it's a higher temperature, the molecule is moving faster than it was before. Here is one. See, my hand is going. See, look at the speed. See, I have to go faster because you're going over a longer distance. Okay, so anyway, how crazy is that? Me sitting there drawing that. But I wanted to show you that's why you have That's why the pressure is the same and the collision frequency. At first, it might be a little higher, but then it will stretch out until it's the same because it's stretching out to match the outside pressure. That's what's going on. And here, the pressure, you got to match the outside. All right, your average kinetic energy will be the same for this example. If I add more gas inside it, that will be the same. Collision frequency is going to be the same. I already broke that down. Energy of impact is also going to be the same. Anything with energy, kinetic energy, velocity, temperature, they're all going to match each other. And the distance between molecules is going to. Okay, let me think about that for a minute. If you add more gas, what happens to the distance between the molecules? You know what? I think it's safe to say it's going to be the same also. Because, did I write the same for volume? No, the volume increases. I'm sorry about that when I went, no, that's this velocity. That is volume. I'm sorry. I wasn't looking at that. Your volume increases. However, since you have more molecules, like before, let's say you had, just say you had like, I don't know what it was. Say you had 4 molecules per liter. Well, now, if you want to stretch it out, you're going to have 8 molecules per liter. It's going to be in a ratio by number. So the distance will be the same between them, between the molecules. When you're adding more gas, they will stretch out. Because the only thing that made it stretch out were the number of molecules there. Okay, now let's do the last one. If you want to see this very last one, what if we change the temperature in a container with a movable piston? And so I'll make that the number of moles up here. And I'll put the temperature here. So I kind of told you this one already. If I increase the temperature, well, look, if we increase the temperature, what's everything that's going to be affected by that directly? We know that the average kinetic energy goes up, velocity of molecules goes up. Having a higher temperature means greater impact when they hit the sides of the container. All right, the number of moles will stay the same. In a balloon, if all you did was change the temperature, like put a balloon into hot air, balloon into a hot environment, okay? The volume is going to increase because now the molecules are moving faster, and so they're going to stretch until their collisions are the same. The pressure will stay the same. The collision frequency, well, I was going to use the same color, or what was I? It stays the same, okay? Collision frequency is going to be the same also. By the time things equal out, it's the same collision frequency. And the distance between the molecules, for this one, since there's no gas added, and since the volume went up, the distance between the molecules will also go up. Okay, wow. It's a lot to think about, but I feel like if you go through this a few times, example, hopefully you'll get the hang of that. So work on that back of the worksheet as well, and we are finally finished with the gas law chapter stuff. All right, I'll see you guys.